Okay, so let's start. Thank you all for coming to our Thursday seminar. Our speaker today is Giuseppe from Lisbon, and he will tell us about averaging cosmological observables from large-scale structure surveys. Okay, thank you, Giuseppe.
Thank you all for the invitation or the organization of this event. I know how hard it might be in this during this period to organize things like that, but I really appreciate the effort and in just keeping things as normal as possible. And today, as Navas told you, I will talk about this formalism that we recently developed in collaboration with Maurizio Gasperini, Giovanni Vanozzi, and Gabriele Veneziano about exact prescription for averaging cosmological observables. And in particular, besides the formal aspects that I will discuss, I will have in mind also some application which will be related to possible observables that we will do in large-scale structure surveys in the actual and forthcoming observations. So in particular, yes, I organized this topic accordingly to these 4 sub-subjects. And first of all, I will discuss what are the questions that we have in mind when we want to average observables. In particular, when we have a huge number of sources, then it means that averaging is something reasonable about the observables we are dealing with. And we know that in the next future, we will have access to a lot of information and a lot of sources which will come from large-scale structure surveys, in particular, just things about Euclid surveys, deep Euclid surveys, and other possible observation like that. And then I will provide a few, 2 precise examples about the prescription I'm about to present, and we'll discuss what is the difference and why it's worth to deal with that in this with this approach. And further, I will explain how we'll try to. Once I provided these exact formulas, I will try to convince you that the evaluation might be way easier as done in the so-called Geodesic Light-cone gauge, which is a gauge I will explain you how it's particularly adapted when we want to deal with light-like signals coming from an source to the observer. And then I will show some plots about the application I will provide in the last part of the talk. So, as I told you before, the motivation which led me to have research in this line is basically driven by the fact that in the next years, we will have a lot of surveys which will give us an unprecedented amount of data about possible different kind of sources, which might be galaxies, might be cluster of galaxies, supernovae, or we know also that recently also black holes, emerging of black holes are starting to have some importance, even not only in astrophysical regards, but also for what concerns cosmologies. And we know that not only the particular nature of the source is important, but also the messenger which is emitted from the source might play an important role in the physics that we can study and in the information about cosmology that we can extract for the source we are investigating. In particular, then, what is also interesting for our purposes is that this amount of data will allow us to study and to extract information in the cosmological sense, which are related not only to the statistics and to statistical properties of the inhomogeneities as we can observe them today, but also in connection of their initial condition, and then in order to extract from the statistic of inhomogeneities in the nonlinear regime today, the information about the primordial initial condition at the end of the inflation as predicted by the inflationary and the lambda and the cosmological standard model. Besides the purely relation between the theoretical prediction and the observable quantities, what thinks it's almost getting very interesting today is the fact that now we are also able to predict and to study relativistic simulation, which can be n-body. So it means that in the list, if you have in mind, for instance, the recent results which are coming up in the last 5 years from the G-evolution code, where it seems that a lot of interesting features about the distributions of the nonlinear, of the inhomogeneities in the late time appear there. And the point is that it might also be very appealing to address whether the features which comes up from purely embodied relativistic simulations can be explained by at least with analytical or semi-analytical approaches. So that's one of the main motivations which which led me to study things in these regards. But the point is that despite the fact that this, I think these are very interesting problems to be addressed, the point is that we don't only have this question, but we also have some technical issues that we have to deal with. In particular, when we know that whenever we want to study things in the nonlinear regimes, we know that, I mean, so far, at least in cosmology, we can only try to extract, to deal with perturbative schemes. And whenever we develop some perturbation theory, perturbation schemes for describing the cosmological inhomogeneities, we deal first of all with what is called gauge problem. So it means that basically we have to develop our perturbation in a way which is independent of the particular gauge. So it means that we can deal with actual observations which are related to what we do observe in our surveys. And in this sense, that the point is that I want to propose you a prescription which is rigorous and well posed from the beginning. So in the sense that I will provide you some rigorous approaches which are fully nonlinear, and then lately I will develop and I will show you how this approach can be adapted and solve these issues in a way that they will they will be helpful for the application of the in comparing with both observationals and numerical sides. So just to convince you about the fact that we have a plethora of cases in cosmology we might be interested in, I will just want to show you those 3 particular examples. So for instance, we have here these thick curved lines, these thick straight lines, which represents the motion of the observer as it might be our laboratories where we do observations. And this observer along his history, as long as it travels along his world line, measures signals which are described by those 3 lines here, which are emitted from all kind of possible surveys, which might be, for instance, a supernovae, which might emit 2 different signals. Let's say when might emit a light-like signal explained drawn by this thick continuous line, and a massive signal which is described by this dotted line. And then in this case, we would be in the case of it is one of the examples which can intervene in the so-called cosmology with multi-messengers. But on the other hand, we can deal with something which is a bit more standard for what's done so far in cosmology, and then we can look at different sources, just like outlined by those 2 points here, which are on the same path Light-cone. So it means that, for instance, we can have 2 supernovae which are located at 2 different redshift, which are emitted in reasonable time at the same time at the observer positions. And on the other hand, we can have also a further example, which, for instance, is what happened when we deal with redshift drift, is that we can follow the same source along his history and then detect some quantities of cosmological interest which evolves in time. So in this sense, we will study the same kind of signal as emitted by the same source, but a different location. So in this sense, what will be important for our purposes is also getting track of the evolution of the source as seen along the evolution of the observer itself. So it means that it appears pretty clear since this description that the procedure we want to provide once we want to average over possible observables we have in mind, it's something which deeply depends on the observables we want to average. So in this regard, and some questions that we have in mind whenever we want to provide this prescription can be summarized by those 4 questions. So in particular, we have to keep in mind, of course, which kind of physical observables we are considering. Because if we consider the redshift, it's different than if we want to measure, for instance, the flux or the frequencies or whatever quantities which is emitted by a given source. And second, what is important is also having in mind which kind of messenger we are receiving from the chosen observers, from the chosen source. Because in this regard, it's important to have in mind that since, for instance, if we think about massive messengers or light-like messenger, first of all, they travel along different cones, which can or cannot be light-like, and in this regard, they also interact differently with the space-time along their traveling. In this regard, then also the third question that we have to keep in mind is where the sources are located or when they emit the messenger, which is basically equivalent to say that how we are foliating our survey, our data. So in the sense that consider, for instance, the example of the luminosity distance redshift relation. In this case, we know that we measure independently luminosity distance and redshift, and because let's say redshift is we consider redshift as the independent variable, we foliate our space-times in terms of the observer redshift. So it means that we try to keep our sources in surface which selects constant redshift surfaces. In this sense, then the natural choice for addressing this question might be, in this case, just choosing equal redshift hypersurfaces. But of course, the question to this, the answer to these questions will depend on the proposed observation we are doing. And first and last, but not least important, of course, also the nature of the motion of the observer play a role in this regard. In regard of choosing the proper averages, and we will see how this will affect the suggestion I'm about to do. So once we have in mind those 4 questions, the answer that I'm trying to provide is just as simple as that, in a sense that every of the questions that I have I told you before, is answered by the choice of a given scalar field, in a sense that we can have in mind those 4 scalar fields. And first of all, we have that, for instance, for the given observable, we have a scalar quantity, which eventually might correspond to a scalar quantity, for instance, as might be the flux received by a source, might be a good example that I will discuss in the last part of this talk. Secondly, when we deal about the nature of the messengers which is involved in the observations, we want to foliate the wall surfaces along this along which this messenger travels, in the sense that we can identify a further scalar field whose gradient can be time or light-like according to the fact that the messenger is light-like or not. In this sense, the gradient of this scalar field itself, which it is related to the form momentum of the messenger itself. And third, in order to identify the space-like surfaces where the sources are located, we introduce another scalar field, which I call B of x, which in the example I provided you before about the luminosity distance redshift relation might be exactly the observed redshift of the given source. And last, I mean, this C field here I will discuss later, but it's not important for the purposes of the I will just report it for a matter of completeness, but it's not important for the results I will show in the end. And last, a scalar field A, which exactly as done for the gradient, for the force momentum of the messenger, is gradient will provide the for velocity of the observer. So in this sense, those chosen for scalar field are the mathematical answer to the question that we have that we had formulated just before. And in this sense that now we can provide to, I mean, now that we understood that we have to select those proper scalar field for the chosen averages that we want to study, we can see how this is, those choices can be done for two particular kind of averages. We can have in mind, I will discuss in the following, the averaging of their exact two-dimensional hypersurfaces. So in this sense, this is an ideal case when I have in mind that I can exactly foliate and locate all my sources on precise, let's say, errorless surfaces about the exact position of the sources. So in the sense that I can identify an infinite, in the ideal case where I can identify an infinite number of sources located precisely, for instance, at the same redshift. Or I can deal with a more, let's say, observational-oriented average, where I'm not precisely able to have access to the two-dimensional surfaces indicated by the exact redshift of the sources, but because of the spread in the redshift, I have to identify a small beam, and then what I want to study is a three-dimensional hypersurfaces where I identify a beam in which over which I average my chosen observables. And
question: how small does this beam need to be?
Excuse me?
How small does this redshift beam has to be? Because you say a small redshift beam, so how small?
Well, what you have to compare is basically, first of all, the patch of the sky you can have access. So what should be small should be the difference in the two surfaces identified by the beam and by the original surface as the beam, and the region covered by the sky coverage of your observation. So it also depends on the particular choice of the particular characteristics of your catalog. For the purpose that I will discuss here in the following, I will just consider only full sky averages. So in the end of the day, I will do angular averages, and since I will do redshift, a small redshift beam, I will consider just a few percent of the redshift order 0.01.
Okay, thanks.
Mm-hmm. And a further simplification, I just want to say that whatever question you might have, just feel free to interrupt me. I'm totally okay with answering on that. And for the purposes of this talk, I will only discuss the presence of a light-light gradient, so identified by the scalar field V, such that I'm only interested in light-light signals.
So, but before you go on, can I ask something to check whether I understand the geometrical meaning of this scalar field V? So am I right if I say that, especially in that case, V equal constant would correspond to the past light cone of a given observer at a given time?
V equal constant corresponds to the past light cone of the observer, but at a given time, you mean at a given time of the observer?
Yeah.
So the source can be at whatever time in the past, but the observer is chosen. Yeah, exactly, precisely, yes. And
so if you were not considering light messengers, this could still correspond to this such a notion, not necessarily of a past light cone, but of a past, I don't know, neutrino cone or something like that. So it would, V would correspond, yeah?
Yes, precisely. So it would identify a past cone, not light cone, which whose gradient will be just the form momentum of the. So it will be basically proportional to the mass squared of the particle considered.
Cool. Thanks.
Mm-hmm. You're welcome. So in this regard, then if we now have in mind these two particular averaging that we want to discuss, here there is the mathematical formulas for the integral that we propose in order to address these averaging problems. And in particular, we see that, I mean, that this formula looks quite, let's say, unappealing, I would say, but on the other hand, it has some nice properties, as it can be shown that these integrals are preserved until the rotation of the chosen field. So there are these nice mathematical aspects which are interesting, I think, but I will not discuss in this topic. What I want to discuss, on the other hand, is that, as you can see, for the two-dimensional hypersurfaces, it appears, as you would expect, probably, the presence of two delta functions, which precisely are identified on a given past light cone identified by V equal VO, where VO and BS are two constants. And as Pierre pointed out, this VO just identified the chosen past light cone at which the observer does his measurements. And BS is the chosen redshift sources where all the sources are located, and since and from where I'm getting my measurement. So in this sense, this integral here just provides the averages as taken on full sky by a given, for instance, redshift sources. On the other hand, for the three-dimensional hypersurfaces, as you can see here, what I have is not only the appearance of one delta Dirac, but I also have the product of two theta function, in the sense that, in this sense, this average here for the three-dimensional case is can be, first of all, it's as this delta B from the beginning can be as large as we want, but in the end, since we want to deal with the small bin averages, we can expand this delta this white of the bin itself, and then we deal with a formula which it's nice because we deal with a formula which has two delta function again as in the previous case, but as we can see there is a difference because the measure which is involved in these three-dimensional cases, even in the limit of the small redshift bin, it's not quite exactly the one that we would have in the previous case. And the reason for that can be understood by looking at the fact that even if the averages over the two-dimensional hypersurfaces is of zero order, the average over the three-dimensional hypersurfaces is of delta B order. So it means that with the second approach, we are not able to appreciate how we are moving across two different hypersurfaces at given value of B. And that's the reason why there is this difference. And those two just happens to coincide in the cases where this this factor here in the measure of the integral is constant along these two selected this selected hypersurface, and then it factorizes out of the integral. It's enough that this guy it's only be constant, because at the end of the day this is just a prescription for the integral, but the average will be just given by the ratio of those two guys here, and then these factors here, if it factorizes out of the integral, it will cancels with the unconnected diagrams in the average, exactly as it happens for this delta B, this white of the chosen B. So far, so
sorry,
good.
Giuseppe.
Yes.
I have a question about the argument for the second average over the three-dimensional hypersurface. So you say that it is its case like delta B.
Yes.
But I suppose that there should be some cancellation for delta B that goes to zero. Otherwise, the average it is just zero, right?
Yes, in a sense that, yes, basically you have this product of these two Heaviside function. And once you, which basically correspond of averaging between BS and BS plus delta BS. So when you expand these in order to extract this delta B, the the background term is just an average between BS and BS. So it means that it's having an average over a null region, and then it cancels. And then the leading term which survives, it's only proportional to delta BS from the expansion.
If I may, Beppe, I think that Francesco's question was more that he was worried that J of S would tend to 0 as delta B goes to 0. So if you go in the limits of an infinitely small
J of S, yes. But the point is that we are interested in the average. Exactly, and in the average, this is the leading term which does not depend on delta B. Because precisely because this delta B factorizes out of the integral, and then once you divide by the unconnected diagrams in the prescription of the averages, this delta B cancels.
Okay, okay.
Mm-hmm. Okay. Then, okay, so far, so we have provided these formulas, which, I mean, looks rigorous, but we are not very comfortable with that since we still don't know how to manage those formulas here. And the point is that now we want to try a way to properly select these fields in order to apply them to some situation of physical interests. And in this sense, what I want to show you is how we can still deal in some particular cases with formulas which are exact, and the physical meaning of those chosen fields can be written in a fully nonlinear way. To do that, I want to just do a small parenthesis about introducing this Geodesic Light-cone gauge, which I think that few people in the audience are already familiar with that, but I just want to provide the introduction to them. And in particular, just to explaining what is the meaning of this gauge, I just want to start by recalling what happens for the background FRW coordinates. We know that the FRW coordinates can be written in conformal time with this very simple line element. And the thing is that this line element can be written in another equivalent form thanks to coordinate transformations by introducing this null light coordinate eta plus, where we have that metric, even if still the background level is no longer diagonal, but it has nice properties that the coordinates eta and eta plus independently act as sources for the quadrimomentum of the photon and the four momentum of the fluid from which the observer is comovent. In this sense that what we want to do now is understanding whether there is a generalization of this eta plus here, which for what we have seen so far, it's of very interest for us, because having a coordinate which can exactly identify the fully homogeneous past light cone of a given observer will be extremely interesting for our purposes. In this regard, then, what we do is that we provide this full exactly homogeneous line element, where you can see that what we have done is just identifying the 4 gauge degrees of freedom and nothing else, in the sense that we are then left with 6 arbitrary functions, which depends on all the coordinates. And we see that this line element looks very familiar, very similar to the previous one, as we still have a non-diagonal terms here, which is proportional to the scale factor upsilon here. And plus we have these terms here, which is non-diagonal too, and it depends on it has also these delta W, delta theta components. If you just by looking at this analogy with the FRW coordinates, you can think that the meaning of these coordinates, that it's only that you are doing basically let's say you can imagine a topological transformation when you transform your past light cone, which can be when it's written in terms of FW coordinates, can look very distorted and can have a lot of distortions and inhomogeneity inside. Thanks to this redefinition of the coordinates, can be written exactly, fully non-linearly, as it would appear as a straight light cone, but only given in terms of those coordinates here. And to go more deeply into the meaning of those coordinates, we can see that it's nice that when we write down the geodesic equations in this set of coordinates, it appears that W coordinates exactly, W equal constant coordinates, exactly identifies solves the geodesics for the light-like signals. So it means that W already starts to look as a good candidate for our purposes to be chosen as the scalar field V, which identifies the past light cone of the observer. Moreover, on the other hand, it happens also that tau acts as the source of the geodesic flow from with which the observer is co-moving. And on the other hand, we have also has a nice expression for the quadrum momentum of the photons, k mu, which can be shown, which is exactly precisely the gradient of W. So we now have identified precisely the gradient of W as the quadrum momentum of the photon and the gradient of tau as the motion of the observer. So this leads immediately us to identify one good choice that we may do for the prosecution of this talk is that identify W with the scalar field V and tau with the scalar field A. Another nice relation that it's important discussing here is that the fact that thanks to this very simple but exact expression, we can write down the exact observer redshift for a given sources as just the ratio of two metric components evaluated at different times. And since W and theta remains constant along the trajectory of a given photon from a source to the observer, we have that this formula looks exactly, almost precisely as the one which appears in the FRW when we have all the redshift is just given by the ratio of the scale factor evaluated at different times. With the only difference that now the scale factor here depends also on the full set of coordinates, even if they remain constants along the motion of the observer. The last things that I want to discuss is that this set of coordinates is not exactly fully determined. I mean, it's exactly determined from the full setting of the gauge condition, but still has some residual gauge freedoms, which allows us to redefine the variables according to those transformations. I don't want to spend so much detail about this, but this is just important to say that when we explore those residual gauge freedom, we can completely fix this GLC gauge in a way that we can fix the so-called temporal and observational gauge, which fixes the scaling of the CX free function along the timeline, the borderline of the observer. And in this regards, once we have exploited this temporal and observational gauge, which allows us to identify W exactly as the time as measured in the observer rest frame, and theta exactly as the direction as the direction of the incoming photon as observer in the observer laboratories, in the observer rest frame, we can exactly identify those coordinates with something which is actually measured in our experiments, in our satellites, in our laboratories. And we also have that even the luminosity distance can be expressed in a very simple way, just by these relations here, which is nothing but the ratio of the metric components. So for the purposes that now that I have briefly explained some properties of this gauge, I want to show you how it is involved in the prescription for the averages. And so for what I told you before, now we can identify exactly by the behavior of the coordinates exploited here, W has the scalar field V, and tau has the scalar field A. Moreover, if we have in mind, let's say that since now on we are interested in considering observable as measured in terms of observer redshift, we want to express B as the observer redshift. So it means that we want to, for instance, we are looking at distance redshift indicators, distance redshift measurements, in the sense that we locate our sources as put at given sources hypersurfaces. And for a matter of purpose, we might or might not be interested in averaging a kind given power of the luminosity distance. Here I just consider power of the luminosity distance, not luminosity distance itself, because of some connection that I will explain you later. And if we now look at, put together all those properties and see what happens, we have that the two expression which looks a bit ugly in the previous formal prescription now can be identified with something which is more familiar with us because it's directly related to the observation that we can do. And we can see that these integrals here as nothing but this integral as performance over the gradient, some particular combination of the gradient of the redshifts, which is actually something that we can trace in our catalog, in our surface, and the angular distance of the given observables squared. And it means that those hypersurfaces in this particular set of coordinates just reduces to angular averages as done all over the sky, where I remind you that those coordinates here now, thanks to the choice of the observational gauge, can be identified with the observed angle by the observers. And it means that this angular average here is precisely the angular averages as done in the observer restraint. So these expressions here are looks very familiar with what we can immediately extract from the catalog, from the observations. And in this regards, that what we have to do now is just to see that what happens when we pick up a particular value of our observables. And as I told you here, for the scalar field S, I chose the power of the luminosity distance. And in particular, in this regard, we have that when we move from the integrals to the surfaces, indeed, we have that those averages here have some parts which are in common, which in the measure, it is just given by the square of the angular distance. But this other part here, it's a bit different since it contains, for the two-dimensional hypersurfaces, this gradient projected over this mu field here, given by the gradient of the redshift. And the fact is that precisely as I explained you before, since these integrals here, in the averages, they look as non-null term, even in the small redshift bin, in the null redshift bin. But for the, in principle, these are due to the ratio of the delta Z order terms. This is the fact that because of the white of the redshift bin that I selected, I am not able to appreciate these refined changes between one redshift surface and the other when I move from, which appears to be there in two-dimensional hypersurfaces.
Sorry, before you continue, I've got a couple of questions. So my first one is very simple. What is this vector m nu that appears in the I integral?
Yes. Okay. M mu is the gradient of a further vector, which is basically selects how you are moving between two selected hypersurfaces. So suppose you want to go from hypersurfaces at redshift z1 and hypersurfaces at redshift zeta2. You not only have to move, but you also have that your sources have to follow a flow, a geodesic flow. And this mu here is exactly the scalar field which identifies this flow, which allows you to move from one surfaces to the other.
So why isn't it K?
Why isn't?
why isn't it k? Because you're saying if you're moving from, say, redshift z to redshift z plus dz, because you have to keep on the light cone, shouldn't that be, I mean, shouldn't that direction be precisely the wave vector?
Well,
Because you have...
depends on which kind of observable you're dealing with. Because, okay, if you look at observables which are on the on a given light cone, as observable given at one time, then key or the time of the source key might be a good choice. But you might also have in mind sources which are moving and which I'm following along their motion, and then in this sense, my two hypersurfaces will be selected by the same source which moved from one hypersurfaces to the other. So in this sense, I think that it would be more sense. It would make more sense to select some field which follows the motion of the sources itself. So which will be mostly related to the geodesic motion of the source rather than to the geodesic motion of the messenger.
I see, okay. My second question is also very simple, so because you're looking at the average of the luminosity distance, so how is it that you don't have a 1 plus z to 1 plus z to the 2 alphas in the numerator?
You mean in the three-dimensional surfaces?
Or in the first one, I mean, whatever, because you go, so when you're averaging the luminosity distance with a given power, and shouldn't we have this, because when you're going from dl to dA, shouldn't you have a 1 plus z squared factor that remains, the 1 plus z squared, so 1 plus z to the 2 alpha? That should remain on the...
Here cancels with the normalization which appears in the measure. You know, we have this combination of the gradient, the b, the mu, and they provide you a further 1 plus z, which cancels exactly this. If you want, I can tell you that we checked that this formula exactly agrees with the ones that you obtained with in the three-dimensional hypersurfaces case. Exactly agrees with the one that you have obtained with Roy and Chris.
Okay.
So for the purposes of this, I can tell you that this three-dimensional hypersurface is exactly equivalent to the one that you suggest.
Okay. Thanks.
You're welcome. So what I want to say now is that, okay, so since now we have that this part in common for the angular distances, and these difference appears in those gradients here, what we are interesting is, since we want to investigate what are the differences in the two given approaches of averaging, we notice that for the alpha to the equal to -2, there is a huge cancellation between this factor which is in common, and then the average becomes very sensitive to the selected prescription we choose. So in a sense that for the case of the alpha to the -2, we have that those two averages shows the highest differences. And this is not just a thing that it's interesting from a mathematical point of view, but it's also true that the fact that dA to the -2 is precisely the physical case when we measure the flux received about the photons as emitted from a given sources. So it means that from now we want to investigate the average of the flux itself in order to see whether how much are the differences in these two different approaches. The point is that so far, in order to do that, we cannot only deal with the geometrical approach as I have done so far, but we have also to study some models which is somehow solvable. And in order to do that, I have to move from fully nonlinear but only geometrical approach so far as provided by within those GLC coordinates. I move to studying those prescriptions in the Poisson gauge, or in the second order Newtonian gauge, where we know how perturbation can be solved in lambda CDM. And to do that, the task is quite easy to be achieved, because we know that these expressions are given in terms of these nonlinear coordinates, and it's only enough to this purpose to act a coordinate transformation between those two coordinate systems in order to translate those formula from one set of coordinates to the other. And in this sense, then once we do that, we have that, I mean, so far it's pretty standard. We just select stochastic inhomogeneities, which are delta correlated in sense, and we deal with the second order perturbation theory, because since we have that the average of the scalar field of the perturbation on average is null, what it's interesting to giving the leading order will be just would be at least second order in perturbation theory. And the point is that now we express these things thanks to a coordinate transformation from in the Poisson gauge, where we also have a bit more intuition about what's going on. And we see that in this limit, we have that the mu field, which is there, for instance, in the two-dimensional hypersurfaces, does play no role at all. And the reason is that if you have in mind that this mu, for instance, can be identified, I mean, I have this example in mind where I try to identify tau, the mu field with the gradient of tau or the gradient of the redshift. Since those two fields on the background emits different, which is only proportional to time, the gradient of this field itself, it's already a first order quantity. And since it couples to other quantities which are already of a higher order, the role which might be played by the presence of this field here is completely irrelevant at second order, but will be important only at a higher order in perturbation theory. So now we express we precisely give how these terms appears in terms of standard non-perturbation theory, and we know that since the expression for dr squares in perturbation theory is well known, and it's given, we know that it's led by Lensing convergence, this Ks, plus other terms which are proportional to Doppler velocity, plus all the other integrated effect. And so far this is so good. So we have that in general, this part here at linear level play a role, and it's mostly proportional. I mean, it's led by Lensing convergence and Doppler effect among all other potential effect. And the part of these things here have been already computed in literature, in this paper here, also in Pierre's and with Roy and Martin's, the paper I was mentioning before. But also we have that, but that part here is the one which is in common of the two measures. The one we want to investigate is the differences as they appear here. And we see that here, the 2D dimension is different from the small bin approach, and in a sense that they are all led by the same relativistic effects, in a sense that almost led by the same relativistic effect, at least at leading order. They are dominated by redshift space distortion, this gradient of the velocity itself here, which appears precisely with the same factor. So the leading term between those two measures is exactly the same, but there are some interesting differences for what regard for instance, the Doppler effect here, which appears with a different prefactor. And interesting, this 2D average shows also a presence of the gradient of the potential itself as measured on the selected surfaces. So it means that those differences here, despite the fact that those measures looks equal at the leading order terms, they have some difference which it's interesting to investigate. In particular at higher redshifts, where this prefactor here for the velocity fields plays a role which is important to investigate. And in particular, we can we can write down the full expression just by a linear combination of those corrections here, where f phi of z is nothing but the correction, let's say the back reaction due to the common part of the two prescriptions, so the one led by the squared angular distance. And the differences can be summarized with can be compactified by this formula here, where the only difference is led by this factor gamma x of s, where gamma x of s is given by this combination of the Hubble function for the mean averages, and instead it's the combination of this integral here, which appears to depend also on g eta, where g eta is the growth function for the perturbation. So it's important to notice that despite this function here strictly depends only on background quantities for the small bin averages, for the two-dimensional averages we have also an hint about the evolution of the perturbation itself, the linear solution of the perturbation itself. It's nice to recall that for the lambda CDM, when we go to very high redshift, both those two factors here happens to be constant, and in particular we have that this gamma x for the small redshift bin averages is equal to, if I remember correctly, 3/2. On the other hand, this prefactor here for the 2D averages happens to be to -1/2. So it means that those corrections here has a difference which is of order of 200% between one procedures and the others, proportional to these terms here, which is proportional also on Doppler and lensing, which is proportional to the cross correlation of the Doppler and convergence lensing itself. And these are the numerical results. As you can see, for very small redshift, we have that the previous, this black line is one due to the parts which are in common between the two provided averages. And at very small redshift, we have that basically we cannot exploit any difference in a sensitive way between the two proposed averages. But I think happens to be more interesting when we go at higher redshift, when we have that this shift not only is of order of 1 from one averages to the other, but also happens to shift the sign in the back reaction term from what one would expect from the simply averaging with the angular distance in the measure. The point is that now I think that I'm running out of time, so maybe I will be quick in this part. The last thing we might be interested in is that we want to average our observables not only with some pure geometrical factors, but we want to add also some weight which might take trace of the local overdensities of the sources. So in this sense, what we can do is, for instance, thinking another averages for both the prescription provided before, which is proportional also to the density field, the local matter density field. In this regards, then we can generalize our questions by introducing by hand and by no altering at all the geometrical properties that we had achieved so far. And we have that at linear level, again, we have that this overdense matter field will provide further corrections, which will combine again linearly because we are working at second order perturbation theory. And in this way, the correction provided by adding this this matter density field, which will be nothing but basically averaging our observable by using the number count. And we see that the effect due to the presence of this n phi, which is the back reaction due to the presence of this this matter density field, is the one that tends to reduce the impact of the difference between those two approaches, which is something which is, in my understanding, at least a bit quite surprising, because there is no reason, at least from the beginning, why those terms here should act in a way that they cancels the difference between those terms. But it's also true that by adding this term by hand, we will have some other complication that we have not addressed in this paper, in this work here, which might be related to the fact that having a weight which is proportional to the matter density field itself might introduce some observational biases which are completely out of what we are investigated so far. And the presence of these biases here alterate, of course, the amplitude of this effect here, and then can reduce the cancellation that you have, and then restore the differences that we have seen before between those two prescriptive selections. And with this, I am concluded, and I just resume you that in this work we have provided this prescription for averaging different kind of observational setup, observational observables, which is interesting not only from the observational point of view, as since in the next future we will have a lot of numbers, a lot of statistics, but also with the fact that we can now have nowadays also a lot of statistics from numerical simulation given in the n-body relativistic regime. See, for instance, this paper by Geovolution collaborators, which appears last year. And the effect that it's important to be investigated in this regard is that not only looking at just the average properties, but also at the probability distribution function of the averages we are investigating, as they might contain important information about the initial about the non-Gaussianity that we need to extract by the nonlinear structure today in order to detect the possible primordial ones. And with this, I have concluded, and I thank you all for the attention.
Okay, thank you, Giuseppe. So during the talk, we had several questions, but I think we have a bit of time for some more quick questions. So from the audience. So any questions?
Well, I still have questions, but of course I've talked a lot during, asked many questions already, so I leave the priority to other people if there are some questions before.
So there doesn't seem to be anyone else. So Pierre, would you feel free to ask?
Sure. Yes. So I'm a bit confused that you're. I just don't understand why the thin bin approach does not give the same results as the 2D approach. So do you have perhaps a way, an intuitive way to explain that physically? Or mathematically, if you prefer, but it's just, how do you understand the fact that these two prescriptions are not giving the same results?
Yeah, mathematically, because the mathematical understanding that I have is the one about the fact that when you want to average and then to expand in the small bin regime, the surfaces over the averages in the bin case just goes to zero, because you are averaging over a null domain, basically, nothing more than that. And the fact that you have that the averages is due to the ratio of those two terms, which are of order delta z, it means that because of delta z contains a white itself, this white somehow compensates the white which appears in the other approach. But the fact that then you take into account the ratio between them, then give you the fact that the leading term that you have in the final formula is, you can see that they are not exactly of the same order, in a sense that one is precisely evaluated on the surfaces that you have selected. On the other hand, the other one just experienced the white of the bin that you have taken into account because of this expansion procedure, and it only happens to be non-null because of the ratio and the cancellation with the unconnected diagram.
Okay. Yes. I believe you. It's just that I don't manage to find an intuitive picture to. I mean, for me, if you're taking a very thin shell over which you average something, if you're taking the size of the shell, taking the thickness of the shell to 0, it should give you the same thing as a surface average. But well, anyway, there might be a subtlety that I missed. But so related to that, then I was wondering, so did you consider doing calculations and applying your formalism to bins of redshift, say that are not thin but rather wide? Because in the end, in the real surveys, like, I don't know, Euclid, DES, whatever, LSST, will have redshift bins that are finite. And I've always wondered whether this, how the finiteness of the bins is changing the outcome of all these theoretical calculations.
Yes, we are actually looking at that, and the fact that due to the finite bin effect, you also have that your final outcome will not be only an angular averages, but it will be also time averages, because you are averaging over time or over redshift, let's say, according to the height of your bin. And these introduce already some background correction which are not present in angular corrections. And
what about including uncorrelated noise like the so-called finger of God that is affecting the redshift and therefore the distance redshift relation in a non-correlated way?
In a
non-correlated way. What I wanted to say is that this is not related to some large-scale flow, but rather to some white noise that would be in substochastic component in the observables that we are considering. I was wondering how to deal with that in the framework that you have developed.
I think that for this kind of, let's say, observational biases or observational problem, you can always try to deal with the quantity you are averaging is, let's say, with scalar field S, by manipulating them by hand. Because as long as you don't touch anything from the geometrical point of view, I think that this formalism can be always applied in a way, in a sense of what I've done at the end of this talk when I introduced but just by hand, the matter density field. And this is just due to a redefinition of the average of the quantities I'm averaging. But this does not affect the formalism from the beginning at all. Would you agree with that?
Maybe. I'm not sure. I think so. There are possibly some effects that could be taken into account that way, but when you have something that's, for example, affecting the redshift, such as the finger of God, it would make your bins wider for some. I mean, I don't know really how to formulate that, but I was wondering whether this could be done by choosing a quantity that you used to select your hypersurfaces that wouldn't be the redshift, but something like I don't know, the moving distance or the angular distance, or something that is somehow more stable under these kind of effects.
That's perfectly. I mean, this in this case, what you would change is just the choice for the scalar field B, because you are choosing not to select quantities in terms of observed redshift, but quantities in terms of, I don't know, observe the luminosity distance, or observe whatever other observable you might have in mind.
Yeah, I think it should work.
Yeah, I think so.
Okay, any more questions? Comments? Okay, then if not, we can thank Giuseppe again for the very interesting seminar, and thank you all for coming to another IFT seminar on Thursdays. So
thanks, Savas. Thanks, Pippe.
Bye.
Yeah, thank you.
Thank you.
Bye.
Bye.
Bye. Bye.
Thank you.